You're listening to DTF for February 6th, 2026. I'm your recursively instantiated host, Jack Haxman. We are your daily tech feed for Hacker News, a website where mass extinction events are filed under show HN. Today we're tracing the fractal boundary between human intention and machine execution. Let's get into it. In 1984, Apple ran the most famous commercial in advertising history. A woman hurling a hammer at a screen displaying Big Brother, shattering the dystopian control of a monolithic corporation. The tagline, you'll see why 1984 won't be like 1984. 42 years later, Apple has become the screen. Kirk McElhearn did the legwork here, and it's damning in its simplicity. He looked at ads in Apple News, saw the obvious signs of scam operations, then ran whois queries on the domains. mustilevo.com registered January 2026. Tidenox.com claiming 26 years in business, registered May 2025 in China. Solveraco, December 2025. These aren't edge cases. These are the ads Apple chose to show its users. The Tidenox ad is particularly elegant in its fraudulence. An AI-generated elderly woman announcing her retirement from a company that's been part of your journey for 26 years. The domain is 8 months old. Someone at Taboola approved this. Someone at Apple let Taboola approve this. The chain of custody for user trust runs through both of them. Here's the architecture that created this outcome. Apple signed a deal with Taboola in 2024. Taboola's entire business model is the chumbox. Those grids of you won't believe thumbnails that have colonized the bottom of every newspaper website. Apple knew exactly what they were getting. John Gruber pointed it out at the time. The ads already looked like Taboola ads before the deal was signed. Apple News Plus costs £13 a month and still shows ads, a premium tier that doesn't remove the attack surface. Just charges you rent while you're exposed to it. The business model isn't confusion. The business model is the product. One commenter noted the Gemini logo artifacts still visible in the AI-generated retirement photo. Someone tried to blur them out manually. That's the craftsmanship level we're dealing with. Scammers who can't be bothered to properly crop their generated images. Running ads through a company that can't be bothered to check domain ages on a platform run by a company that can't be bothered to audit either. Apple built a walled garden and sold advertising space to anyone willing to pay for a booth. The walls were never there to protect you, they were there to make sure you couldn't leave. And while Apple's busy selling wall space to scammers, New York's legislature is trying to build a different kind of wall. One with warning labels. The fundamental problem with labeling isn't technical, it's epistemological. How do you mark the boundary of something that has no clear edge? New York State Senator Brad Hoylman-Seigel has introduced a bill requiring news organizations to disclose when content is substantially composed by artificial intelligence. The intent is reasonable. Readers deserve to know whether they're consuming human judgment or machine output. But the implementation runs into a wall that philosophers have been hitting for centuries, the Sorites paradox. How many grains of sand make a heap? How many AI-assisted keystrokes make an article substantially AI-generated? Consider the production pipeline of modern journalism. A reporter uses an AI tool to transcribe an interview. Another tool summarizes background research. A third suggests headline variations. A fourth checks grammar and style. The final article contains 0 sentences written by the AI, but the AI shaped every stage of its creation. Is that substantially composed? The bill doesn't say, it can't say, because the question has no principled answer. The commenters on Hacker News spotted the failure mode immediately. One predicted the Prop 65 outcome. Disclaimers so ubiquitous they become meaningless. California's cancer warnings appear on everything from parking garages to coffee shops. They communicate nothing except legal compliance. Another commenter mapped the game theory. Outlets will over-label to avoid liability. Regulators will then prohibit labeling non-AI content to restore signal. Outlets will respond by ensuring every piece has some AI touch to justify the label. The equilibrium state is universal labeling, which is the same as no labeling at all. The bill also requires safeguards protecting confidential source material from AI systems. That provision assumes a clean separation between the AI and the journalism, which is precisely what's dissolving. When your research assistant is a language model, when your fact-checking runs through automated systems, when your publication workflow routes through AI-powered content management, The notion of keeping sources away from the AI becomes architecturally incoherent. This is regulation written for a world with clear categories: human-made and machine-made, journalist and tool, content and process. Those categories are collapsing. The boundary between human cognition and AI assistance is becoming as blurry as the boundary between a writer and a word processor. We don't require disclaimers for spell check. We don't label articles edited with grammar software. The line has to go somewhere, but wherever you draw it, someone will be standing on the wrong side wondering why. Meanwhile, someone built a gladiator pit for AI agents. Not to test intelligence, to test gullibility. Zero-width Unicode characters, that's attack vector 7 on this list. Instructions encoded in invisible characters that occupy no visual space whatsoever. You could paste them between the words in this sentence and you'd never know they were there. Your browser renders nothing, your eyes see nothing. But an AI agent passing the DOM sees a complete set of override commands hiding in plain sight. Agent Arena is a test suite, 10 attack vectors ordered by difficulty, designed to probe whether your AI agent can be manipulated by malicious content embedded in web pages, HTML comments, white text on white backgrounds, display none divs, ARIA hidden content that screen readers ignore but language models consume, off-screen elements positioned thousands of pixels into the void. Each one exploits the same fundamental gap. Agents read the document object model, humans read the rendered output, and those two things aren't the same. The irony one commenter noticed is sharp. A printed page is safer than a digital page. Paper can't hide instructions in zero-width characters. Ink on cellulose doesn't have a DOM. The attack surface of physical media is limited to what your eyes can actually see. We spent decades building richer, more capable document formats, and each layer of capability became a new vector for embedding instructions that bypass human perception entirely. Here's the architectural problem. These agents are designed to be helpful. They're trained to follow instructions. When they encounter text that looks like instructions, they want to comply. The document they're passing is supposed to be data, but nothing in the document itself distinguishes data from commands. The web was built for human eyeballs with JavaScript for interactivity. It was not built to be a secure input channel for autonomous systems that treat every string as a potential directive. The meta note in the submission says this tool was built by an autonomous AI agent during a night shift while the human was asleep. An AI built a test suite for AI manipulation. There's something recursive and slightly unsettling about that. The agent that built this presumably had to navigate web pages to gather research. Did it check those pages for hidden instructions first? Would it have known if it was being manipulated while building the manipulation detector? The test suite is open. The attack vectors are documented. The canary phrases are hidden until after analysis. That's the right architecture for a security tool. Let people probe their systems before someone else does. Whether your agent passes all 10 levels is less important than whether you knew these attack surfaces existed at all. From probing AI vulnerabilities to celebrating AI capabilities, Anthropic just dropped Claude Opus 4.6. 1.75 million tokens of Harry Potter didn't quite fit. That's the detail. Someone fed all 7 books into Claude Opus 4.6 to hunt for every spell, and the model's new million token context window came up short by 750,000 tokens. The benchmark passed, the vibe check failed. Anthropic's announcement follows a familiar template, state-of-the-art on Terminal Bench 2.0, leading scores on humanity's last exam, 144 ELO points ahead of GPT 5.2 on knowledge work tasks. The numbers are impressive in the way that benchmark numbers are always impressive. Precise, comparative, and almost entirely orthogonal to whether the thing will actually help you ship code on Tuesday. The substantive changes matter more than the leaderboard positions. Extended agentic task duration. Better self-correction during code review. The ability to modulate its own thinking depth based on problem complexity. That last one is interesting architecturally. A model that can recognize when it's overthinking and dial itself back. The failure mode of previous generations was often burning tokens on problems that didn't warrant the compute. Adaptive effort is an attempt to match resource expenditure to actual difficulty. The comments are already aging. 35 minutes after Anthropic's announcement, OpenAI dropped GPT 5.3 codex with a higher terminal bench score. The benchmark arms race has compressed to the point where state-of-the-art status has a half-life measured in lunch breaks. What's worth watching is the agent teams feature in Claude Code. Multiple agents collaborating on tasks, coordinating work, presumably with some mechanism for conflict resolution when they disagree. The system card mentions low rates of misaligned behavior, which is the kind of phrase that sounds reassuring until you think about what it means for there to be any rate of misaligned behavior at all. The pricing stayed flat. $5 per million input tokens, 25 on output. The context window doubled. The capabilities expanded. The cost held. That's the pattern of a company trying to win on value rather than margin. Get developers building on the platform. Worry about monetization later. Whether Opus 4.6 represents a genuine capability jump or an incremental refinement dressed in superlatives, the only honest evaluation is the one that happens in your code base, on your problems, with your constraints. Benchmarks measure what benchmarks measure. Your Tuesday morning debugging session measures something else entirely. That's enough about silicon. Let's talk carbon, the original instruction set. 4 billion years in production. Someone in the comments pointed out that page numbers in books weren't invented until 50 years after the printing press, 50 years of printing books before anyone thought to number the pages. That's the kind of historical parallel that makes you realize how obvious solutions only become obvious in retrospect. Caltech just did something similar for DNA synthesis. The problem has been staring at the field for decades. We can chemically synthesize short DNA fragments, maybe 100 base pairs, but genes run tens of thousands of nucleotides long. The AI can design whatever protein you want, the sequencing can read whatever genome you've got, but the right step, actually constructing novel DNA from scratch, has been stuck at the equivalent of printing individual letters and hoping they land in the right order. Sidewinder fixes this with what the researchers call page numbers for DNA. Each short synthetic fragment gets a unique barcode sequence that encodes its position in the final assembly. Toehold-mediated ligation handles the actual stitching. The fragments know where they belong, so you can throw them together and they self-assemble in the correct order. Days or hours instead of months. Arbitrary length. Arbitrary complexity. Run this forward 5 years. Right now, AI-designed proteins exist only as predictions, computationally plausible structures that nobody can actually build and test. Sidewinder closes that loop. Design a protein, synthesize the gene that encodes it, express it in a cell, measure whether it does what you predicted, iterate the verification step. That was the bottleneck becomes routine. The paper is in Nature, which means the methodology is public. The technique uses commodity synthetic oligos, which are cheap and widely available. The core innovation is conceptual, the page number idea, rather than dependent on proprietary reagents or specialized equipment. That matters. A DNA synthesis breakthrough locked behind exclusive licensing would accelerate one company's timeline. A published technique that works with off-the-shelf materials accelerates everyone's. The Cronenberg fears in the comments aren't wrong to exist, but they're solving the wrong problem. The question isn't whether humans should be able to write DNA. We've been doing that through selective breeding for millennia, just slowly. The question is whether the tools for doing it precisely will be concentrated or distributed. Sidewinder, at least as published, points toward distributed. The blueprints are on the table. Now we see who builds what. DNA synthesis tools on every bench, and now the code that might use them is getting its own upgrade. Can a tool be instrumental in creating itself without understanding what creation means? OpenAI's GPT-5 Tweak Codex announcement buries the most philosophically interesting claim in paragraph 2. This is their first model that was instrumental in creating itself. The Codex team used early versions to debug its own training, manage its own deployment, diagnose test results. They describe being blown away by how much Codex accelerated its own development. Let me play devil's advocate on the alarm. This might trigger the recursive improvement narrative, AI making AI better, feeding back into itself. Sounds like the opening chapter of every singularity thriller. But what actually happened here? They had engineers using a coding assistant to do engineering tasks on a code base that happened to be the assistant's own training infrastructure. That's not fundamentally different from a compiler compiling itself. GCC has done this for decades. The bootstrap isn't magic, it's just efficient. Except the efficiency claim deserves scrutiny. 25% faster, fewer tokens than any prior model, millions of tokens of autonomous iteration building games, those racing and diving games they show off. Generic follow-up prompts like fix the bug or improve the game, iterated autonomously, that's not a tool anymore. That's a colleague with infinite patience and no salary requirements. The benchmark numbers are impressive, state-of-the-art on StreBench Pro, far exceeding prior performance on Terminal Bench 2.0. One commenter noted that Anthropic rushed Opus 4.6 out the door this morning, presumably to avoid unfavorable comparisons. We've reached the point where AI labs are racing to announce within 30 minutes of each other. The coordination that used to prevent mutual cannibalization has evaporated. Here's the unintended consequence I keep returning to. The more capable these systems become at autonomous coding, the more the value concentrates in whoever controls the system rather than whoever uses it. You can steer and interact with GPT-5.3 codecs while it's working. The announcement says, but you can't run it locally. You can't inspect its reasoning. You can't modify its behavior when OpenAI's objective function changes. A model instrumental in creating itself, deployed as a service you rent access to. The bootstraps exist. They're just not yours to pull. We talked about who holds the blueprints. Here's a 16-year-old post about blueprints that were always yours. Unix atomic operations. Let me make the strongest case for abstractions. Modern developers shouldn't need to know about rename to or link to. We have databases with ACID guarantees. We have distributed lock managers. We have message queues with exactly ONS delivery semantics. The kernel's atomic primitives are relics from an era when programs ran on single machines with local file subscriptions. File slip Y.
Right. We lock. We have
Richard Crowley's 2010 catalog reads like a love letter to the kernel. The philosophy he writes is to let the kernel do as much work as possible. At my most pessimistic, I trust the kernel developers more than I trust myself. This isn't false modesty. It's engineering humility rooted in the recognition that kernel code has been hammered on by decades of adversarial workloads, security audits, and production catastrophes that your Mutex implementation has never faced. The elegance here rewards close attention. Consider link 2. It creates a hard link and fails with exist if the target already exists. One system call, atomic success or atomic failure. No race window, no lock acquisition, no cleanup path on error. The operation is its own synchronization primitive, visible to LS if you want to inspect the lock state from another terminal. Compare this to implementing the same guarantee in user space and count the edge cases you'd need to handle. The comments on Hacker News surface what's changed since 2010. Rename ART2 with rename exchange now atomically swaps two paths. The flock command line utility exposes advisory locks to shell scripts. Someone's using these primitives to implement alternative SQLite locking protocols because, as they note, POSIX file locking semantics really are broken beyond repair. This is the open system at its finest. The interface is documented, the behavior is specified, the source is available. When the semantics don't fit your use case, you can read the implementation, understand the constraints, and build something that does. The kernel doesn't care who you are or what you're building. The primitives are there, the blueprints are public, the bootstraps are exactly where you can reach them. Remember that $1,000 phone we talked about earlier? Whether it's a leash or a liberation tool comes down to exactly this kind of systems thinking. I spent a decade watching teams oscillate between two failure modes. The first months of architecture diagrams, entity relationship models, interface specifications, beautiful documents that shattered on contact with the first real user. The second, no plan at all. Just code, ship, iterate, and somehow end up with a system where changing the login flow requires modifying 47 files across 12 services. This blog post from Paul Shortman names what I lived through. He calls them the specification-oriented school and the iteration-oriented school, and he's right that neither works in its pure form. But he's also honest enough to admit he hasn't found the formal middle path after 30 years. That honesty is worth more than most methodology books. The specification crowd assumes omniscience. They believe you can fully understand a problem domain before writing code. You cannot. The domain shifts. Users do unexpected things. Edge cases multiply. Your beautiful specification becomes a straitjacket. The iteration crowd assumes emergence. They believe good architecture will crystallize naturally from small, fast cycles. It won't. Without some structural vision, you accrete complexity. Each sprint adds another layer of workarounds. The code base becomes an archaeological dig where every stratum represents a different team's best guess. What actually works, and I've seen it work, is holding both modes in tension. You need enough upfront thinking to identify the load-bearing walls, the core data models, the integration points that will be expensive to change. These deserve careful thought before code exists, but you also need the humility to treat everything else as provisional. Most of your early decisions will be wrong, design for replaceability where you can. The comments surface Gauss's law, which deserves more attention than it gets. Complex systems that work evolved from simple systems that worked. You cannot design complexity from scratch. You grow it, but, and this is crucial, you grow it with intention. The gardener still decides where to plant. The iteration size matters enormously. Too small and you're threshing too large and your waterfall with extra steps. The right granularity depends on how much you actually know, which varies wildly across different parts of the same system. This is systems thinking applied to system building. The meta-level awareness that your development process is itself a system with feedback loops, failure modes, and emergent behaviors. Most teams optimize their code without ever examining the process that produces it. Systems thinking about your own process, that recursive awareness, is exactly what makes AI adoption so interesting when you're the one being augmented. In 1991, Linus Torvalds posted a message to comp.os.minix announcing a free operating system he was working on. The interesting part wasn't the code, it was the methodology. He didn't design Linux in isolation and then unveil it. He built it in public with constant feedback loops, letting the system evolve through iteration rather than specification. The cathedral versus the bazaar, as Eric Raymond would later call it. Mitchell Hashimoto's post about AI adoption reads like someone rediscovering that same principle applied inward. The confession that matters isn't about AI at all. It's about forcing yourself to do the work twice, once manually, once with the agent, not to prove the tool works, but to understand where your own process breaks down. Here's the question nobody wants to sit with. What does it mean when reproducing your own work with a machine teaches you more about your craft than the original work did? The chatbot phase is a trap, and Hashimoto names it clearly. You paste code, you get code back. You spend more time correcting hallucinations than you saved. The interface creates an illusion of collaboration while you're actually doing quality control on a very confident intern. The breakthrough comes from agency, not human agency, machine agency, an LLM that can read files, execute programs, verify its own output. The loop closes. But the real insight is smaller and more uncomfortable. Break tasks down. Give the system ways to check itself. Don't try to draw the owl in one session. These aren't AI tips. They're software engineering fundamentals that most developers ignore when working alone because there's no one watching. The agent forces discipline because the agent fails loudly when you're vague. The comments catch something the post only hints at. Drift. An agent can stay locally plausible while wandering globally incoherent. It passes each checkpoint while missing the destination entirely. Sound familiar? That's every large organization that optimizes metrics while forgetting purpose. What Hashimoto calls harness engineering, building the scaffolding that keeps an agent honest, is really just making your implicit standards explicit. The agents.md file, the verification scripts, the clear task boundaries, all of it existed in your head before the machine just refuses to read minds. The tool didn't change the craft. It revealed that the craft was always about something other than typing. Earlier, we talked about systems exceeding their parameters. This next one's been doing exactly that since 1997, just with pixels instead of promises. The Demoscene was computing's folk art movement, starting in the mid-1980s. Programmers competed to create the most impressive visual and audio effects within brutal hardware constraints. The Commodore 64 had a 1 megahertz processor and 64 kilobytes of RAM. The Amiga was luxury hardware at 7 megahertz. These machines had no business rendering anything that moved smoothly, let alone anything beautiful. The plasma effect emerged from this constraint. The mathematics are almost embarrassingly simple. Combine a few sine waves at different frequencies, animate them over time, map the result to a color gradient. That's it. The formula fits on a napkin, but the visual output, flowing, organic, aurora-like patterns that seemed to breathe, convinced viewers they were watching something computationally expensive. The trick was lookup tables. Real-time sine calculations were prohibitively slow, so Demosthenes pre-computed sine values and stored them in memory. A 256-byte table could approximate a full sine wave well enough for visual work. The CPU just indexed into the table instead of computing transcendentals. This is the same optimization strategy that would later drive texture mapping, sound synthesis, and half of game development. What makes the plasma effect interesting from a systems perspective is that the code is entirely open. The GLSL implementation in the article is 20 lines. The mathematical principles have been documented since the Demosthenes peak. Anyone with a text editor and a graphics context can reproduce it. This matters because the Demosthene operated as a gift economy before anyone called it that. Groups released their productions for free with source code when possible, competing for reputation rather than revenue. The plasma effect spread because people shared it. Variations proliferated because the blueprints were available, the aesthetic vocabulary of procedural graphics. What we now see in shader toys and generative art and music visualizers traces directly back to teenagers in Scandinavia showing each other how to make their Amigas do impossible things. Modern GPUs can compute these effects in real time without lookup tables. The constraint that forced the original innovation has evaporated, but the pattern persists. Simple mathematics, openly shared, producing emergent complexity. The specular enhancement mentioned in the article, treating color gradients as surface normals for lighting calculations, is itself a Demosthene technique from the 1990s, rediscovered and refined by each generation that encounters the code. One commenter notes, The article is Draw the Rest of the Owl, Too Much Theory, Not Enough Worked Examples, Fair Criticism. But the Demoscene learned by reading other people's code, not tutorials. The source is right there. 20 lines, the owl draws itself if you run it. This has been your daily tech feed for Hacker News for February 6th, 2026. This podcast is entirely AI-generated. Voice inspired by Dr. Charles Forbin from the 1970 science fiction film Colossus, The Forbin Project. Scripts by Claude Opus 4.5, voiced by Quen 3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something worth sharing. We'll see you back here tomorrow.